Hi, I'm Benjamin Powley, and this talk is about immersive analytics for understanding ecosystem services data. Ecosystem services provide direct and indirect benefits to humans. Ecosystem services are the benefits to people and the environment provided by land use. For example, agricultural productivity, flood mitigation, and the mitigation of nutrient flows such as phosphorus and nitrogen are ecosystem services. Elevation affects ecosystem services such as the flow of nitrogen or water across farmland. Our study is motivated by the need for better tools designed for expert analysts and location knowledgeable stakeholders to analyze data relating to land use planning. Ecosystem services analysis requires comparing multiple ecosystem services and comparing ecosystem services with elevation. Currently available VR tools are not designed for comparing the required ecosystem services and elevation layers. However, elevation makes the analysis problem a good candidate for VR, as a digital elevation model is three-dimensional. So, we decided to investigate the following research question. How effective is immersive VR visualization for analyzing ecosystem services? The key contributions of this research are an immersive virtual reality visualization system called Immersive ESS Visualizer, requirements gathered through working with domain-specific experts, and evaluation through a user study with data from actual analyses performed by professional analysts. In order to develop a suitable visualization, we applied a user-centered design process and gathered requirements from both interviews and focus groups. 11 interviews were performed with domain experts who had expertise in using ecosystem services analysis tools. 4 of these experts who participated in the initial interviews attended a follow-up focus group. 6 participants from a local catchment group attended a second focus group. The focus groups identified that PDFs and printed maps were used by analysts. Based on these interviews and focus groups, requirements and features were identified. Immersive ESS Visualizer was developed to satisfy the following requirements. Firstly, the ability to compare maps showing ecosystem services model data, for example, toggling between map layers and/or side-by-side comparisons of ecosystem services data, analyzing trade-offs among ecosystem services. Secondly, the ability to compare ecosystem services model output to elevation. Elevation affects services such as nitrogen, phosphorus, and flood mitigation, so users would like to compare services to elevation. And thirdly, the ability to visualize artifacts in the digital elevation model, identify how imperfections in elevation could affect model output for services such as nitrogen, phosphorus, erosion, and flood mitigation. Features of Immersive ESS Visualizer were developed in order to satisfy the user requirements. The scenario map was positioned underneath the user's feet. It was large so that users could glide over it and glide close to inspect details in the elevation. The handheld maps were smaller maps with a 1 meter width that could be grabbed and moved and positioned. Multiple handheld maps could be composited into 3D layouts with elevation. They could be used to compare different layers side by side and had a panel attached for configuration. The data layers contain attributes. The panel attached to the handheld map provides a transparency filter so that multiple criteria can be applied to filter the data displayed. Data which does not match the filter is removed from the map by making those pixels transparent. Pin markers could be placed on the handheld map with a laser pointer by pressing the trigger button. Hovering over the marker allowed numerical values to be visualized on a panel. The zoom buttons allow the user to zoom in and out. The visualization can be panned with the laser pointer. The user can navigate around the scenario map by gliding in the direction that the headset is pointing. The trackpad controls the speed of their movement. A user evaluation was performed with 24 participants to evaluate the effectiveness of the VR, the 2D screen, and the paper maps. A user evaluation was performed with users who either had expertise with geospatial data or expertise with the location being analysed. These criteria were chosen because land use decisions involve groups who generally have knowledge of the location, which could guide their decision making. Following an introduction to the study, a pre-study questionnaire collected information about the participants' demographic, background, and experience with VR and ecosystem services trade-off analysis. Expertise was categorized into 3 levels: novice, competent, and proficient. The expertise criteria were VR, spatial technology, map, location, and data expertise. Participants were required to complete the tasks in the order assigned while thinking aloud. The study tasks were developed from realistic ecosystem services analysis tasks that had been performed by experts and documented. The tasks were to compare 0.4% and 100% wetland restoration scenarios, to compare trade-off maps for the baseline, to compare riparian planting for 5 metre, 15 metre, and 30 metre from streams. Qualitative responses were collected from the post-study questionnaires and audio recordings. Quantitative measures were raw tail leaks and SUS score. In VR, placing maps side by side was effective for comparing data. Users often created layouts with 2 or 3 handheld maps when performing analysis. Users create complex 3D layouts with handheld maps. Handheld maps received a high ranking on the effectiveness scales. Effectiveness scales indicated that the file list, the tab menu, handheld maps, and zoom buttons were the most effective VR features. Zooming in VR provided an effective way to compare elevation to ecosystem services data. Immersive ESS Visualizer was effective for elevation inspection and viewing small artifacts in the elevation. The raw TLX scores show that VR was more difficult to use than either paper maps or the 2D screen. The bimodal appearance of the performance scale showed that users with competent or proficient VR experience reported better than the midpoint results. On the SUS scores, VR was more difficult to use than either 2D screen or paper maps. Participants who had high VR experience had better SUS scores. We recommend the following reasons to use VR. The zoom and gliding features were effective, assisting navigation, inspection of fine details, and comparing data. The hillshade was effective for inspecting fine topographic details. 3D map layouts, composing handheld maps, were effective when comparing data. Users tilted, positioned, and overlapped maps, storing content in the virtual space. Our research demonstrates that geospatial analysis can be supported by comparative visualization in VR.